Ladies and gentlemen, welcome back to the shop. Today we're going to continue a series on what I'm just going to call the ultimate maker's guide to making things with gears. If you haven't seen part one, I would encourage you to click on this link that's going to pop up right here and you can go straight to that video and watch that one first. You're also welcome to hang out here and check that one out later. Today we're going to pick up where we left off, but before we get into the worm drive, I also want to talk to you about how to design gears for custom projects. Like if you want to have 3D printed or laser cut gears in your projects, how do you even go about laying out the gear profile or arranging the gears, spacing them properly? I've picked two projects, a CNC table saw that I built about 2 years ago, and this laser cut custom design clock that I made. Actually, I think that's a good place to start. So let's go have a look at the 3D model. This is a clock that I designed a couple of years ago, and the whole purpose of this is to be a decorative piece that would keep time. So there's a lot of things that went into this, and this is a good example for talking about how I lay out gears, but we're not quite ready for that. First, we need to talk about how to make the gears themselves. And to do that, I want to show you the gear generator here in Solidworks. Now, if you don't use Solidworks, I have something for you. I'll come back and talk about how to generate gears. And if you don't have a CAD package at all, I have something for you as well. So just give me a minute to talk about this and we'll come back and answer those other two. Now, in SolidWorks, you could design your own tooth gear profile and make a pattern that goes around at the right diameter, but you can also use the gear generator tool, which is built right into the task pane of SolidWorks. My task pane is hidden because I like having a lot of space on the screen, but we can show it by going to View, Toolbars, and then down here you'll see Task Pane. Over here on the side, you see this panel opens up. If we click on the library books, down below you'll see something that says Toolbox is not added. I'll click Add, and then there you go. That installs the toolbox so that you can access all the goodies that are in there. We're going to look under ANSI Inch, and then Power Transmission, and finally Gears. There's a whole bunch of other stuff in there to automatically generate fasteners and so on, but we're focused on gears right now. So let's start with a spur gear. We're going to right click on gear and hit create gear. And that's going to open a new part window, and you can see this configure components dialog box pops up. I'm just going to lock it over here. And then there are various properties that you can adjust. These will change slightly depending upon the type of gear. So if you're making a helical gear, there's going to be some more variables there. In fact, I'll show you those as well. Let's start with diametrical pitch. Diametrical pitch is basically the number of teeth divided by the pitch diameter of the gear. And I know that sounds confusing, so the easiest way to explain that is just to show it to you. So let's go back to my clock for a moment. And here you can see this is the gear train that drives the hour hand, and I have a sketch right behind it. So I'm going to flip that on, and you can see that there are two diameters here, and this circle represents the diameter of this gear where it interacts with the other gear. That is the pitch diameter. If you take the number of teeth and divide it by that diameter, you get diametrical pitch. But to oversimplify things, we can just think of this number as a way of adjusting the strength and size of the gear. There's more to it than that, but for our purposes, if you want the teeth to be a little stronger, you can decrease this number. By decreasing this number, you have fewer teeth per diameter, and thus the teeth themselves are thicker and stronger. But if you need to decrease the overall size of the gear, you need to increase this number. And what you're doing is you're adding more teeth per inch of diameter, and therefore the teeth are smaller, the overall gear size is smaller. The trade-off is the teeth will be a little weaker, more fragile, things like that. Again, that's a simplification, but that's basically how you will use this number. Here I've created an assembly where these two gears have overall the exact same variables. The only difference is this big one has a diametrical pitch of just 2, and the smaller one here has a diametrical pitch of 20. So for every 1 inch of pitch diameter on this gear, there would be 20 teeth, and for every 1 inch of pitch diameter on this one, there would only be 2 teeth. And that's why this one is so much larger in order for them to both just have 10 teeth. Next up, we have the number of teeth. Your primary purpose for the number of teeth is to set up your gear ratio, but you can also use this number to manipulate the overall size of the gear. So let's just say, for example, we want our output speed to be 1/3 of the input speed. The input gear is going to be the smaller of the two, and the output needs to be 3 times the input. In this case, if we make it 12 teeth, actually it'll let you go down to 10, and then your output gear needs to be 36 teeth. But you can also do 20 and 60, for example, and you still have 1/3 gear ratio. So you can push these numbers around to get the overall size gear that you want to fit within your project. Next, we have pressure angle. If you know what that is, you can tinker with that number. I suggest you leave it at 20. Face width is the width of the gear. That's this distance right here. And this is another way that you can make your gear teeth stronger. Increasing the thickness of the gear gives you more surface area to push on. And so the gear can be stronger by being thicker or by tinkering with the diametrical pitch, which will make each tooth wider at the root down here. And then we have hub style. So if we put a hub on one side, this is your hub. This is the area where you can add a set screw or do various things to be able to hold on to this gear and attach it to the shaft. So hub diameter is this diameter here. Since we're talking about the hub, I want to pause here and talk about just how important this connection is between the shaft and your gear. This joint needs to be able to handle all of the forces coming through it. It's part of your powertrain. And so if the gear can slip on the shaft, you won't be able to transmit the power. There are a whole bunch of different ways to make this connection. It might be a set screw, which is going to be one of the weakest possible connections. You can use a key, which is really strong because you have literally put a blockage in between, and the strength of the material itself has to shear off. The key has to shear off in order to allow them to slip past each other. Sometimes you see both, where there's a key and a set screw. And then there are all sorts of other options. There are collars that are split with clamps so that as you use screws to tighten them down, it actually squeezes the shaft tighter and tighter with the clamp. So there are many ways to approach this, and I won't cover all of those in this video, but I do want to say it's worth taking the time to think carefully about this joint, especially if you need to transmit a lot of power. Now, in my clock, for example, the forces between the various gears is very low. You really only need enough force to be able to move all of the gears on their respective shafts. So in some cases, I didn't even put a hub on the gear. I just used the thickness of the wall and actually put a set screw in between one of the teeth. So that's an option. But just keep in mind, the greater the torque you need to transmit, the more carefully you need to think about how you join your gear to the shaft. One of the more extreme examples might be actually welding your gear to the shaft, but then you lose the ability to disassemble, or you're going to have a really messy disassembly. So this is just something worth taking the time to think carefully about. Now, the rest of these are pretty self-explanatory. Shaft diameter is just like it sounds. It's that the hole for the shaft that'll hold your gear. Keyway, again, another way to grip onto the shaft. And then that's pretty much it. When you're done, you just click the checkbox, and then you've just created a part, and now you've got a gear, right? And you can take this part and put it in a gear assembly. If you choose helical gear, let's right click and hit create part. The variables are mostly the same with a couple of little differences. One of them being the helix direction. This one is left-handed. If you're going to mate two gears together, then they need to be opposite hand to each other. So here we have an assembly of helical gears. Both of these gears are right-handed, and you can see the teeth interfere. They don't mesh properly. But if you made it with a left-handed gear, right-handed, left-handed, they mesh properly. And that's why you need to have opposite hand gears for helical gears. But what if you don't have access to Solidworks? How do you generate your gear profile? Well, there are a couple of different options. You can do a quick search online, and there are actually some free gear generators that will give you similar parameters. You put in diametrical pitch and the number of teeth and fill in the various parameters, and then it will spit out for you a DXF file or something that will allow you to create the profile of your gear. Those are freely available, so you just have to search for them. And of course, another option would be to just switch over to SolidWorks. Now, I laugh because a few years ago, this was not exactly a practical thing for a hobbyist. You know, this is the industry standard for CAD tools. But now they have 3D Experience SolidWorks for makers, which is just incredible. It's got all the powerful tools that you get from SolidWorks, and it's accessible. It's like $48 a year to have access to the most powerful CAD tool on the planet. And SolidWorks is the only tool that I've used for this pretty much since the beginning of my channel. I think there's only one video where I didn't use Solidworks, and it was the very first one, but it gets better than that because they created a special link for me, which gives you an additional 20% off. So now it's $38 a year. So you get CAD and CAM, you get XDesign, XShape, all these powerful tools that are on their website. And I've made videos and tutorials about how to use these different CAD packages. So even if you are a complete beginner, there's so much help available online to get you started, including some of my videos. So I strongly recommend that you give it a try. It's solidworks.com/Jeremy Fielding to get 20% off of the maker offer. The bottom line is this is the most powerful tool that I use to design my projects, and I strongly recommend you give it a try. solidworks.com/Jeremy Fielding, and you'll get another 20% off of the already low price of $48. So at this point, we've made our individual gears, but now I want to give you some tips and tricks about how I assemble them in my various projects. In this case, I'm going to focus specifically on gears, but if you want more design advice for how to make your parts stronger, cheaper, easier to make, on and on, I have a whole video dedicated to that. I'll put a link in the description. And there's another separate one specific to 3D modeling. So it's like 50 tips and tricks for CAD design. And I'll also put a link to that one in the description. But I want to start with my clock because it has a lot of gears. The first thing you want to think about, tip number one, is what do you want these gears to do? In my case, I want them to be attractive, number one, because this whole piece is about putting gears on display. And I want it to eventually tell time. So the gear ratios need to be right to make sure that the hands spin at the correct rate. With that in mind, let's look at the clock. I mean, you can see that all the gears are very thin because the forces are very low here and everything's moving really slow. But even with this very slow speed and low force, I still have some bushings in there, as you can see here, because I didn't really need a bearing, but I did want it to slide pretty smoothly, and I didn't want that hole in the wood to eventually wear to a bigger hole, so I put a bushing in there to reduce wear for the wood. And that theme is all throughout the clock here. There's some transparent pieces in here. So some of the pieces are made out of acrylic. This support wall is made out of acrylic. Specific to gears, I want to show you the planetary gear in the back. So let's do a section cut here. Now, the next video in this series, we should be covering the planetary gear, so I'm not going to talk about it much here, but I will name the parts. These are the planets, which revolve around that gear, which is the sun. This is the yoke, which is controlling the position of the planets as they revolve around the sun. And this gear is called the ring gear. The ring gear is stationary. It's not going to move. You can design it so that your ring gear can move. We're going to come back to that later, though. There's a lot of gears, and they need to all be positioned and meshed properly. So how did I do that? Well, what I do is I think about each layer of the clock. So layer one is back here, and I have a sketch associated with that. I just turn the sketch on, and you can see there's some sketch lines in the back there. Looking at this sketch, you can see its relationship to the gears. This circle is representative of the ring gear. This one for the planet. This circle here for the sun, and so on. So let me just hide the parts so that we can only see the sketch. And then its purpose will come clear. This is literally what I start with. I've already designed my planetary gear, and I want to figure out how am I going to hold on to the sun, the planets, and the ring gear and keep everything in the right position. Well, I start with this sketch. What makes this sketch so powerful is because one circle gives you the two most important variables about the gear: its pitch diameter and its center of rotation. If you start with a sketch like this, you can immediately see exactly where these gears need to be to mesh properly. And then you can add your parts into your assembly. What I usually do is mate this gear concentric with the circle, with the sketch circle, and then all the gears are now in the right place. Once you've done that, then you can start thinking about how are you going to hold on to all these pieces so that they're in the right spot, right? And so I started designing this back wall here. I cut some big holes in it because I wanted to be able to see through the clock from the back and from the front. And that gives you a good starting point for designing all of your connection points and how you're going to hold on to all these various pieces, and also allow the pieces to move the way they need to move. I mean, that's what the yoke is here for. It needs to constrain the planet to this circle, right? This circle where the yoke is. But the gear needs to be able to spin on its own axis, and it needs to be able to roll inside of the ring gear. So you get the idea. And then each layer is designed exactly the same way. So if we turn on layer 2, now that we're looking at layer 2, you can see there's a similar set of sketches there. And this can get confusing if you try to show it all at the same time, but just for the sake of driving home the point, you're now looking at layers 1 and 2. They're all sketched on the front plane, but we can turn on each layer as we need to lay out all the gears. And this is a two-dimensional way of positioning all of your gears properly to make sure that they mesh with each other correctly. You can also use this method for a rack and pinion. It's just that the rack has a straight line, sort of like an infinite diameter, along where the rack's pitch diameter is. And then you need to make the pitch diameter tangent to that line. So for example, if this is the pitch diameter of your rack, and then you're going to have a gear rolling along the rack, you need to take this, make it tangent to this, and then you got it. That gear will roll along that rack all day. Okay, there's one more tip I want to show you here in the clock, and that's related to the number of teeth and diametrical pitch that we were talking about earlier. I had this one problem that I struggled with for a while in the back of the clock, and that was at layer 2. If you look here, you can see there's a little gear, and I needed a 6-to-1 gear. I mean, that was even got 10 teeth, and like I told you earlier, I normally don't go below 12, but I really needed to get 6-to-1, which means this one should be 60. And it is. And so I needed to position this gear, and this gear. This one has to be directly in the center line of the clock because it's connected to the yoke. This one has to have a mounting point that falls on this back wall, but you can see I've got some big holes there. What I did is at first I started manipulating diametrical pitch. Changing the diametrical pitch affects all 3 of the gears, and changing the number of teeth for this center gear affects both of these gears. And so there's a really interesting challenge here. And what I ended up doing is after I had felt that I had manipulated these as best I could, I went back to the back wall and I added these little bulges that you can see here, which gave me just a little bit more surface area to add in the mounting point for this gear. And then there you go. So sometimes even manipulating multiple numbers, it can be a challenge to get the center of the gear exactly where you want so that you can support it properly. And here I was able to just nudge that wall out just a little bit in order to make that happen. So here's my CNC table saw with the automatic fence on the top. I also automated the blade tilt, which is the mechanism you see here with gears. And this is the mechanism that lifts and lowers the blade. So each one is a little bit unique in that over here on the fence, we have the rack and pinion. The plate's hidden so that you can see where the gear would be. Oh, there's no gear in there. I guess I didn't model it. But anyway, there will be a gear on this shaft that's designed to mesh with this rack. That rack and that gear are made out of steel. Those are purchased components. Down here, I needed the gears to be strong enough to tilt this mechanism and slide all of that left and right, as well as move the whole motor inside of the system for tilting the blade, because all of that stuff moves together when you tilt the blade. So I used a 1-to-1 gear ratio, but you can see that the teeth here are relatively thick. These are 3D printed gears, but they're printed at 50% infill. And the way I figured out how much force I needed was I actually attached a fish scale to the handle that was here before. I pulled on it and then I could see how much torque was needed in order to spin this wheel and move this whole mechanism. And then I knew how strong the motor needed to be and how much force the gear teeth needed to be able to handle. Now that method may sound complicated when you can't see it, but it's actually really very simple. And I made a whole video explaining it. I will put a link to that video for you in the description. And similarly here, the force needed to lift the blade up and down wasn't very much at all. And so these are 3D printed gears, but it's relatively thick, as you can see. And I think there's a 2-to-1 or 3-to-1 gear ratio. You can see the smaller gear right there. And this whole mechanism was actually pretty interesting to design. These slots allow me to slide this mechanism up and down to adjust the fit between this gear and the other gear. It lets me tighten the set screw in there. I can change that bottom gear if I want. So quite a lot of thought went into making these 3 pieces, but they're all 3D printed pieces. But those are the main things I wanted to show you here, is that you can use different materials, different thicknesses, and there are all sorts of things that you can play with to make sure the gear can do the job. All right, this looks like a good break point, so we're going to pick up in the next episode with the worm drive. If you haven't seen part 1, I'm going to put a link to the playlist right down here below me. You can click on that, and not only will that let you see part 1, it'll also show you part 3 when that video is available. Thanks for watching.